Hello and welcome to this presentation. This presentation is about simple harmonic motion. This is the higher level simple harmonic motion. In fact, this is the first lesson of the wave phenomena topic, which is an AHL, additional higher level material topic. We're building on topic 4, waves. In topic 4, you should have been introduced to simple harmonic motion, and you might recall the important points, which is firstly that it is an example of a periodic oscillation, something that happens repeatedly, something that can be described in terms of words like frequency, how often it happens, how many times per second, and period, the number of seconds that an entire oscillation lasts for. So it's a type of a periodic oscillation, but in particular it has a defining characteristic, it has a defining equation in fact. And that is that the acceleration of the object that is in simple harmonic motion, if there is an object, because this same mathematics can be applied to things like fields and variations in fields, but let's deal with physical systems such as a pendulum or a mass on a spring. And the acceleration of that object will be proportional to the displacement. So the displacement is the distance from the equilibrium position, and minus a is proportional to minus or negative x, because the acceleration and that displacement will always be in opposite directions. As the displacement goes in one direction, the acceleration will be back towards the center. As the displacement goes in the other direction, it will be back towards the center. If it obeys that principle, it's simple harmonic motion. Now we can describe simple harmonic motion using an equation. A model based on circular motion. Many similarities between the two, as I will show you shortly. But I'll briefly describe what's happening here. This is a diagram illustrating a frozen moment in time, obviously, as all diagrams must. And the yellow blob represents our object. And we'll say it's going around in circular motion with a constant radius r, constant in magnitude at least. Like all circular motion, the acceleration is directed towards the center. There's the angle, theta, which changes with the time. And v is the linear or tangential velocity of the object. Omega, on the right hand side there, is the angular frequency or angular velocity, and it is the number of radians per second that our object is rotating with. The period, t, as I've said, is the time taken for one complete rotation. And y is the vertical displacement from the equilibrium position. Sometimes we'll use an x because that's more what you should use, and that's what's in the data booklet. But I've put y, at least initially here, to illustrate the fact that it is the vertical component of the radius. Now a couple of definitional questions, equations, which we'll come back to later. Omega equals 2 pi over big T. 2 pi is the number of radians in the circle. T is the time taken to go around the circle, so the period. So that is the radians per second. V, the linear velocity, is the circumference, 2 pi r, divided by T, the period. But since 2 pi divided by big T is omega, the angular velocity, then V equals omega r. Excuse me. And A equals V squared over R. We got that from the circular motion equations, which also, if you do a little substitution, equals V squared divided by R. So our Y value, as our object rotates, the Y will go up and then down and then negative and then back up again. It will oscillate. But will it be simple harmonic motion? Will the acceleration of that object, that projection of that object at least, will it be obeying the laws of simple harmonic motion? It's a periodic oscillator, but will the acceleration be proportional to the negative of the displacement? Now, this lovely little video illustrates the point here. On the left hand side we have the object going round in a circle, and also you can see projected onto the vertical axis is that vertical component of the radius. Let me play the video. So you'll see it spinning round, you'll see the vertical component illustrated, but you'll see how that vertical component matches the mass on a spring oscillator, which has been introduced as an example of SHM. So this very strongly suggests it is SHM. And on the right hand side we have a graph, so this is projected that vertical displacement is projected along a time axis. Very nice. So is it SHM? Does it obey that the acceleration is proportional to negative the displacement? Well, let's have a look at a little bit of a closer look, which we can see here. Now, I'm doing this to kind of avoid calculus, because the IB doesn't require you to have calculus to do DP physics. So we're taking a more graphical approach, and for that let's identify some common angles. So theta is the angle between the radius at this point in time and the horizontal axis, and we can draw additional thetas as shown on the diagram there, which are going to be the same angle. We'll use those in a minute. But let's start by looking at how the position or how the value of y changes with time. Omega equals theta divided by little t, so the angle change divided by the time taken. So theta equals omega t. So anytime you have theta in an equation like this, you can replace it with omega t, which will tell you, which you can use to calculate the value of theta at a particular moment in time. Now, by simple trigonometry, y equals r sine theta. So you can replace the theta with omega t, and we have y equals r sine omega t. So there you go. That's our first equation right there. And that tells you how y, the vertical displacement, varies. It will vary with the sine of omega with respect to time, multiplied through by r, because r gives you the maximum. So sine omega t will vary between minus 1 and 1, but r multiplying through that, because r, when y is its maximum extent, when the circular blob is at the top, that will be r. That will be the amplitude. Y equals r sine omega t. In terms of the velocity, so that's the position. In terms of the velocity, then just from the graphical, from the similar angles I talked about, the vertical component of the velocity, Vy, equals V cos theta. V equals 2 pi r over t, or omega r. So we can replace that with omega r to get Vy equals omega r cos omega t. Those of you who've done some calculus, by the way, might spot a connection here, because any velocity is just the differential of the position. So same. And again, using similar angles, ay, the vertical component of y, equals negative a sine theta. Why the negative? Because if you look at the diagram, I've drawn it in the opposite direction. So I have the opposite to the acceleration vector. A equals omega squared r. So ay equals negative omega squared r sine omega t, but r sine omega t is y. R sine omega t is y, so we can replace that in the equation to give us ay equals negative omega squared y. So we have our three equations. One equation for position and how it changes with respect to time. Position in terms of a vertical displacement. One equation in terms of velocity with respect to time, and one equation of the acceleration, which is actually with respect to the position. And the equation for simple harmonic motion, which we've looked at and defined before, is a equals minus omega squared x, and I hope you can see that they're basically the same, because y is just a displacement and x is a displacement. That displacement is a maximum when x equals x0. Okay, so that here corresponds to when y is the same as the radius, when it's vertically up down on my diagram. So we can replace that up there at the top, as you can see. And so instead of having y, we have x. Instead of having r, we have x0 to represent the maximum value. So we get x equals x0 sine omega t, v equals v x0 cos omega t, and a equals minus omega squared x, which are three of the equations on the in the data booklet for this topic, and they relate to the position, velocity and acceleration of an object in simple harmonic motion. Going back to that velocity equation to just develop one more of it, so v equals omega r cos omega t. Now you don't need to know this derivation, by the way, but it's nice to be able to see that it is there. It's not just being made up. Basic Pythagorean identity, cos squared theta plus sine squared theta equals 1, so cos theta equals square root of 1 minus sine squared theta. Notice there's a cos in there, so I can replace that with 1 minus sine squared, and so we get v equals omega the square root of r squared minus r squared sine squared omega t, but y equals r sine omega t as we specified, so it's v equals omega r squared minus y squared. But don't forget that r is really the maximum displacement, whereas y is the displacement at any one point in time, so we can replace those two to get v equals omega x naught squared minus x squared. Now the maximum velocity is when the displacement is nothing. If you think about the pendulum, the maximum velocity is as that pendulum swings through the equilibrium position. At the equilibrium position, x, the displacement from equilibrium position, equals 0. So you get v equals omega square root of x0 squared, which obviously square root squares cancel. So the velocity maximum equals omega x subscript 0. Maximum velocity equals the angular frequency multiplied by the amplitude. Not in the data booklet, by the way, but useful. Good to remember. Okay, so there's a lot of bump in there, but basically we've introduced these equations here and here. These are variations of those equations because sine and cos are the same thing effectively. It just changes where your starting position is for your oscillation. And the velocity equation here. Things will become a bit more clear when we do some questions, which we'll do in a minute. And then the next presentation will also look at the energies involved, particularly this equation here, and that will really expand what we can talk about when it comes to solving problems involving simple harmonic motion. Okay, thank you very much.